Hello, and welcome to this video on integer partitions. Here's what we are going to do today. We will define the concept of an integer partition and then give a few different ways to represent them. One of the nicest ways to visualize an integer partition is as rows of boxes. We will then explore some remarkable identities that involve mappings which convert one type of integer partition into another. And many of these mappings will have a very visual component to them. Rather than starting with the definition, I decided to show you all of the integer partitions for the numbers 1, 2, 3, and 4. You can see that the integer partitions of an integer are just the ways to write that integer as the sum of other positive integers. And I'm actually curious about the number 0. Does the number 0 have an integer partition? It turns out that the answer is yes, and this is an example of the one way to do nothing phenomenon that we encountered in our last video. This will be more clear once we look at the official definition of an integer partition. An integer partition of n is a multiset of positive integers whose sum is n. And a multiset is a set where repeated elements are allowed. This means that the empty set is a valid multiset. And this is why the empty set is the unique integer partition of 0. Elements in a multiset are not ordered, and so we usually list the parts of an integer partition in weakly decreasing order. Here are 4 different ways to represent an integer partition. In addition to writing the integer partition as a sum or as a list, we can give the type of the partition or give a visual representation using a Ferrers diagram. In a Ferrers diagram, we create a row of boxes corresponding to each part. So 3 plus 1 is represented by a row of 3 boxes, followed by a row of 1 box. The type of an integer partition is a list that tells you the number of occurrences of each size. So for example, the integer partition 3 plus 1 has 1 part of size 1 and 1 part of size 3. Meanwhile, the integer partition 1 plus 1 plus 1 plus 1 has 4 parts of size 1. Here are all the integer partitions for 1 through 8, courtesy of Wikipedia. These Ferrers diagrams of boxes are a really nice way to explore integer partitions. Many integer partition bijections proceed by moving boxes around to create related Ferrers diagrams. And here is the definition of the type of an integer partition. And this algebraic notation is a little intimidating, but again, the idea is pretty simple. For example, 2 7s plus 1 3 plus 4 2s gives us an integer partition of 25. So the type of this partition is 0410002. This algebraic encoding of an integer partition can be really useful in some circumstances. Here are the 3 symbols that we use to count integer partitions. Pnk is the number of partitions of integer n into exactly k parts. P sub kn is the number of partitions of n into at most k parts. And finally, P of n is equal to the number of partitions of n into any number of parts. And here is a fun fact. Pn is the hardest number to count that we've encountered so far. It can be shown that the number of partitions of n grows like e to the square root of n. So it is larger than any polynomial, but it is smaller than any exponential function. And take it from me, that's a very weird in-between place to be. Super polynomial, but sub-exponential. This weird growth rate is yet another way in which integer partitions are hard to count. Let's get back to more concrete ideas and explore some of the relationships that are revealed by representing integer partitions as rows of boxes. Given a Ferrers diagram, one natural operation is to flip it over the diagonal. We can see the effect of this flipping on the 5 integer partitions of 4. 4 maps to 1 plus 1 plus 1 plus 1, 3 plus 1 maps to 2 plus 1 plus 1, and 2 plus 2 maps to itself. This brings us to our first partition identity. The number of partitions of n into k parts is equal to the number of partitions of n in which the largest part has size k. This statement becomes quite intuitive once you look at an example using Ferrers diagrams. Here is a partition of 10 into 5 parts. When you take its conjugate, you end up with a partition of 10 whose largest part is 5. The general proof works the same way as this example. Conjugation is its own inverse, so this mapping is a bijection. Okay, let's do a more complicated identity. The number of permutations of n into distinct odd parts is equal to the number of self-conjugate partitions of n. Looking at some examples will really help us to understand what this theorem is saying. Here are the 2 partitions of 8 into distinct odd parts, and here are the corresponding 2 partitions of 8 that are self-conjugate. And similarly over here for n equals 9. There are 2 partitions of 9 that have distinct odd parts, and there are 2 self-conjugate partitions. These partitions are paired up so that they map to one another, but I actually think it's pretty hard to see how this mapping works. So I'm going to color the boxes to help you to see what's going on. I've added 3 colors to these diagrams, and now you can track how the distinct odd parts map to the self-conjugate partitions. Can you see how this mapping works? I want you to pause the video and see if you can figure it out. Try to explain the mapping in 1 or 2 sentences. I hope that you had fun thinking about how to convert a self-conjugate partition into a partition with distinct odd parts. I'm going to give you a sketch of the proof using the example that you see here, and after that, I will give you an outline of the general proof. In my explanation, I'm going to start with this self-conjugate partition. The first thing I'm going to do is to focus on the outermost L shape of the self-conjugate partition. And notice there are an odd number of boxes in this symmetric L. I'm going to peel off these boxes and straighten them into 1 row of odd length. So now I have 1 odd row, and then I have a smaller self-conjugate partition to deal with. This means I'm creating a recursive argument. So let's repeat the process. Look at the largest L shape, peel it off, and straighten it out to create our second row. We need to do this 1 more time to create our final row of length 3. And that's our algorithm for turning a self-conjugate partition into a partition with distinct odd parts. Here is an outline of the details of the proof. We define a recursive mapping that takes us from self-conjugate partitions to partitions with distinct odd parts. The 4 steps listed here are precisely the ones that we used in our example on the previous slide. We strip off the largest L shape and straighten it out to create a row of odd length. We repeat until we have processed all the boxes in the self-conjugate partition. Now we still would need to explain why this works, in particular, why the L's get smaller and smaller so that they each have different lengths. After that, our next step is to prove that our mapping is a bijection. We do this by describing the reverse function and then proving that these 2 functions are inverses of one another. And so if I started with a partition into distinct odd parts, I would go to the top row, bend it at its midpoint to create an elbow L shape. We would then bend the next row at its midpoint and nestle it into the existing elbow shape. We repeat this until we have processed all the rows. We do really need to confirm that this is the inverse function, but I will skip those details for now. This brings us to today's u-try problem. The integer 2 has 2 partitions and neither of them is self-conjugate. I want you to prove that n equals 2 is the only positive integer that does not have any self-conjugate partitions. In other words, I want you to construct at least 1 self-conjugate partition for every n not equal to 2. And I'll give you one little hint. You will need slightly different arguments for odd n and for even n. So good luck and have fun.